Swayam Prabha. Digital India. Educated India.
Welcome back to the manufacturing automation course. So, let me remind you that overall what we are talking about is the automatic assembly system, and in the automatic assembly system, as we said, that we can have the inline type or the rotary indexing type, and the basic problem that we may have in the automatic assembly is the feeding of the small engineering parts. So, those small engineering parts are fed very large number, and the basic problem is that all these parts have to come in a right orientation. So, keep in mind that there is no human being involved here, and the parts are stacked in the bowl, okay, and they can be stacked in a very different orientation, and those parts have to come from the bowl, out of the bowl, through the delivery chute in the right orientation. So, that is what we are now talking. Our job is to feed the parts in the right orientation. So, therefore, if the parts are not coming in the desired orientation, so we have to either reject the parts or we have to reorient the parts. So, therefore, in the earlier class we have discussed the part orienting devices, and those part orienting devices, as we said, that they can be either active or passive. Okay. Active orienting devices are such that they will actually reorient the parts, all right, and put the parts in the desired orientation on the track. And if it is the passive orienting device, so they cannot reorient the parts, but they actually reject the parts if the parts are not coming in the desired orientation. So, based on that we have the differentiation, we have the two groups of the orienting devices, in bowl system or in bowl tooling or out of bowl tooling. So, I am just summarizing that what we have discussed in the earlier class, that the in bowl toolings, they can be passive or active, and they are normally kept inside the bowl. So, they can either reject or reorient the parts. We have seen some of them. So, one of them was slot, which was the active orienting device, others like wiper blade, like the slot, like the cutout, V cutout or the scallop. Okay. Those were the passive orienting devices, because they reject the parts. Now, we have seen that the orienting device shape and the type of the orienting device actually should be according to the parts. For example, we have discussed parts like here, as you can see, the headed parts. So, the headed parts, it is better when the headed parts can actually be fed hanging on the head if that orientation is the desired orientation. Or as you can see that here we have shown that these are the washers, and then for these washers it is only a ledge which is sufficient. We have seen the parts with the heavier side and the open side. So, we saw that the scallop is very suitable for a parts to go through when it is coming with the closed side or the heavier side down. Or we have seen parts like where we have the difference in the diameter at the top and at the bottom. So, for them again that V cutout is convenient for the parts the lower diameter with the smaller diameter up. Or for example, we have the U shaped parts that we have discussed. So, for them if they can ride on the rail, that is very convenient. So, a rail can be designed, for example, on which they can ride, or we can have, for example, the parts like this we have not discussed. So, this is another arrangement of the orienting devices. So, this is the narrowed track, all right, and the track is being narrowed by a wall projection. So, as you understand from this device, from this arrangement of the orienting device, that because of the narrowed track, the parts coming with this orientation and the parts are like this, that they have the two different diameters, all right. So, the parts coming with this orientation will be rejected, because this diameter is not able to negotiate through the space between the narrowed wall, under the narrowed wall and the track, whereas the parts coming in this orientation, this width will go inside the space between the wall projection and the track, and it will go through. Okay. So, let us say that this is the desired orientation for us. So, all parts which are coming through the wiper blade, which are not in this orientation or not in this orientation, they will be rejected through the wiper by the wiper blade, and these parts, when they are coming after the wiper blade, parts with this orientation will be rejected because of the wall projection. So, here there are two orienting devices, wiper blade as we have discussed earlier, and this is the wall projection or the narrowed that makes the track narrower. So, this is, both of them are the passive devices, because they are actually rejecting the parts. Look at this arrangement of the orienting device. Suppose we have the orienting device for a rectangular part like this. Okay. So, here what happened is that there is a narrowed track, and that narrowed track has been done by a different orienting device. Now, this kind of orienting devices, that is narrowed track or V cutout or scallop, they can be as a block, for example, they can be inserted here. So, as you can see from here, that this is the arrangement which is made here. Through this you can actually put the block like this, so that the track can be narrowed, or you can put a V cutout, for example, or a scallop, for example. Okay. So, in this case, for these rectangular parts, if the rectangular part is coming in this direction, it will go through, it will come from here, but in this narrowed track it will be unstable and they will be rejected. So, the narrowed track is a passive device, and all the parts which are in this direction, in this orientation, they are the desired orientation for us. So, these kind of parts will go through, because this is the width of the part which will be able to negotiate this narrowed track, and they are all going through. So, employed to orient parts lengthwise end to end while permitting only one row of pass. Okay. Now, while analyzing the orienting system, suppose we have a part like this, where the weight at this side is more, or this side is heavier, because the part is such where we have a central hole, we have a blind hole, and therefore, this hole is closed here. So, this side is heavier than this side. So, when such parts are being fed, so before we design the orienting device, orienting system, now what happens is we have to find out that what are the different orientations the parts can have. So, normally a soft aluminum floor is arranged, and those parts are randomly, at random they are thrown to that soft aluminum floor at a random basis, okay, and seen that after being thrown from a certain distance, of course, and after being thrown, how those parts are resting on the soft aluminum floor. See, so for example, suppose our desired orientation is this, that is the heavier side down, all right. So, the parts which are coming, they can have 4 orientations, as I discussed earlier. One orientation is, let us say, A, where the heavier side is down. Another orientation is where the heavier side is up, or the heavier side can be to the left, or the heavier side could be to the right. So, these are the 4 basic orientations that this kind of a part can come here. So, suppose if we use a step and we design the step in such a way that most of the parts coming in the orientation A will not be affected, as you can understand that when they are coming here with this orientation, since this side is heavier, so they will simply fall and remain in this orientation after falling from the step, because the step height is designed in such a way. Now, many of the parts which are coming either in the orientation B2 or in the orientation B1, they will actually be, some of them will actually be reoriented in the orientation of A. For example, suppose we have the B1. So, most of the B1 after falling from the step, it can actually fall like this and it can remain in this orientation. If it is coming with this kind of this orientation B2, for example, the B2 can be toppled and this may become C in orientation C, or it may actually become, because this side is heavier, it may fall in such a way that it will be in the orientation A. Now, after the step, there is a cutout here, scallop cutout. So, through the cutout, the parts with the orientation C will not be able to go through, because this space inside diameter, open diameter, okay, inside open space cannot be able to negotiate this space and they will fall. Okay. But the parts which are coming with the heavier side down, for example, they will be able to negotiate, because the the bottom is closed, there is no hole, it is a blind hole as I said. So, it will be, those parts will be able to negotiate and they will go through, and that is the desired orientation here, all right. And then it will come here, and this is a sloped track with ledge. This ledge is protecting the parts from falling down, and all the parts with this orientation A will be going through. Now, suppose this is the sector of a vibratory ball feeder, and let us see how this scallop can be made. Okay, the scallop cutout, because you cannot make that scallop randomly, and it has to be made depending on the shape of the parts, and since we do not want this internal diameter to negotiate, so we have to see, we have to find out that what is the shape and what is the size of this internal diameter, and what is the type of the movement that the parts are making on the track of the vibratory ball feeder. Okay. So, here is a diagram which is showing that how the parts are moving along the track of the vibratory ball feeder. Let us see here. The part starts making from this point. So, as we said that if the dimensionless normal track acceleration, if you remember, a n by g n is more than 1, we have shown that theoretically, then the parts will hop, it will leave the track, and it will, because of the torsional force, it can actually go ahead. So, parts will jump, hop, and it will go like this. So, after falling to the track of the vibratory ball feeder, it will actually go ahead a little bit, parts sliding forward, and then after sliding forward it will actually go back. This is because of the type of the motion or the type of the vibration that is imparted on the parts located at the track. Once again, the type of the, I have shown that earlier, that there are two types of this. One is this vibration, okay, another is this vibration. So, because of the because due to the combination of these two torques, these two kind of torsional torques, so the parts will go hop like this, it will go ahead because there is a torque here, and then it will come back, okay, and then again it will start hopping and it will go forward like this. Again it will behave the same way, part slides forward and then backward and then again jump and so on. Now, let us see that this hop from this point to this point is, let us say 2.72 millimeter for certain amount, certain value of the frequency, amplitude of frequency and amplitude of vibration, and certain value of the vibration angle. Let us say vibration angle normally used is 20 degree. Okay. So, for that let us say this hop is 2.72 millimeter. All right. Then after falling on the track, it will go ahead by, let us say 0.86 millimeter. Okay. Then it is going back, and going back is 0.91 millimeter, and then the effective hop that we are having, although it is 2.72 hop the parts are actually having, but because of the forward movement and coming back, that is the backward movement, the effective hop that we are having is 1.75 millimeter. So, knowing this information and knowing the internal diameter of the part, we can actually design this scallop cutout, which is a passive device, so that the parts with the open side down cannot negotiate this scallop and they fall, because these are the passive devices. So, they will reject the parts, they will not be able to reorient the parts. Okay. Whereas, the step can be considered as an active device, because in the steps many of the parts in the different orientations, they are actually reoriented to the desired orientation, let us say heavier side down. So, therefore, the steps can be considered as an active device. Now, let us now discuss the out of bowl reorienting devices, and I will remind you that out of bowl reorienting devices are always used outside the vibratory bowl feeder, and they are normally active orienting devices, because if had it been passive orienting devices, the parts will be rejected, but the parts cannot go to the bowl back, because these parts have already come out of the bowl and now they are going to the assembly system, to the assembly machine. All right. So, let us say this is a feed track, I will or the delivery chute, let us say. Okay. So, parts have come back, come out of the bowl feeder, and now the part orientation we desire is the heavier side down. So, the parts are such that center of gravity will be here, all right, and if the parts are coming either with this orientation or with this orientation, okay, they will hit the bridge here, which is located in the delivery chute, and after hitting the bridge, since the center of gravity here is the below and the heavier side will be down. So, the part will be reoriented with the heavier side down, and it will always come out of the delivery chute with this orientation, with the heavier side down. Meaning that if the part is coming with the heavier side up, for example, it will hit here and it will be reoriented, because the heavier side is here and the center of gravity is at this point. Or for example, from the feeder, the parts are coming in different orientations, the same parts, let us say, with the heavier side up or with the heavier side down. So, when it is coming with the heavier side up and we want the parts to come out of this delivery chute with the heavier side up, heavier side down, in that case we can put a pin here, and when it is coming from the feeder, it will hit the pin like it was in the bridge case. So, then they will be reoriented, either they are coming with the heavier side up or with the heavier side down. Both ways they will actually, after hitting the pin, they will come with the heavier side down only, which is the desired orientation. So, this is another example of the active orienting device, which are used normally, as I said, and as out of bowl tooling. Here is an interesting out of bowl reorienting device, okay, and these devices are used for cup shaped parts like this. Okay. Here is a kind of a cup shape. So, what we have in the reorienting device is this is a selector wheel, this is called the selector wheel system, and here we have, this is a stationary outer casing, and inside that there is a selective wheel or a selector wheel, which has the grooves here like this, okay, and this selector wheel rotates or indexed in the sense that inside the housing the selector wheel will rotate and dwell for some times, okay, when they are coming or when they are aligning to the exit. Let us say this is the exit and through which the parts can come. All right. Now, when from the feeder the parts are coming either with this orientation, that is the open side up, or with the open side down, they will be coming here and they will fit into this protrusion if they are coming with the open side up. So, open side up will go in and there is a protrusion here, and when it is rotating like this, all right, it will come, this position will come here through this, and it will be retained here, it will not go down, because as you understand that this has climbed here, this is in the protrusion. All right. So, then with the further rotation, okay, when it will come to this exit, this will be stripped off from here and the part will go, and let us assume that this is the right orientation as we desire. The desired orientation out of the delivery chute, the way that this part will be assembled in the assembly machine is with the open side up. So, at once again let us say this example, that part will come like this, all right. Then while rotating it will go to this position, but here there is an exit, but it will not come because the part is located or part is held by the protrusion. So, it will go further, this protrusion will not be able to hold anymore the part, and the part will be stripped off, part will go here. Now, let us take another example. For suppose the part is coming like this with the open side down. When it will come to this, it will be in this position, right. That means, since the open side is down, it will not be held by this protrusion, but it will be located in this way. So, when it will go from here to here, the part will come down because it is not held by the protrusion, the part will be stripped off and it will come here, and again when it is coming, the part will be in this orientation, okay, with the open side up. So, that is our desired orientation. Therefore, all the parts, whether they are coming to the orienting device with this orientation or with this orientation, always will be getting the parts with the orientation which is desired, which is the closed, which is the open side up. Okay. Now, this consists of a stationary container, as I said that this is the stationary container, in which a wheel, this is the wheel which is the selector wheel, this is mounted with radial slots, these are the radial slots, all right. This wheel is driven by an indexing mechanism, because when this position will come here, it has to stop for some time, so the part to be stripped off and part to slide down the slot and going to the delivery chute. So, this kind of indexing mechanism may be a Geneva wheel, for example, Geneva mechanism for example, that we have discussed earlier, to ensure that slots always align with the chute, meaning that slot this either here or here, the slots have to be aligned. So, these are the two exits, one exit is here and one exit is here. So, from where the parts can actually slide down the slot and to the delivery chute. So, this is also a simple mechanism, but very effective mechanism for particular parts. Here you cannot reorient or feed parts of any other kind which are not of the cup shaped. Okay. So, therefore, again I will repeat that reorienting devices can be designed depending on the parts, and it is very easy to design, because you know the part configuration, and then you can say that out of the existing orienting devices you can combine them, you can select one of them, or you can design a new orienting device for that part to be reoriented to make an active device, for example. Now, next topic that we will be discussing here are the feed tracks. So, let me tell you what are the feed tracks. Like we have discussed the bowl feeders, different kind of bowl feeders. So, those bowl feeders are feeding the parts, and the bowl feeder cannot be located very close to the assembly machines, because parts which are coming out of the bowl feeder, they have to go to the assembly machine for an assembly. So, since it cannot be located very closely, so there has to be some path through which the parts will go to the machine. So, those are called the feed tracks. All right. Here are some of the examples of the feed track. This is to provide easy access to automatic workheads and the assembly machines. Part feeders are usually placed some distance away from the workhead. Now, for example, here this example you can see that this is for the cylindrical parts. It is a very convenient and very easy design. This is open here, and through this the cylindrical parts are being fed. Here the flat parts. So, this kind of a flat part is coming, this is the clamp, okay, and this side is open, this is the rod which is preventing these parts from coming out, okay, and through this slot the flat parts will be coming from the bowl feeder to the machine. Or for example, for screws. For screws, what we can do is you can have a slot, as we have seen in one of the reorienting devices, and the parts may actually hang in the slot and come out. For example, this is the example which is shown here. Part tracks connect part feeders to workheads of assembly machine, and here is the part track which is for the headed parts, like in here. Okay. So, these are the spaces which are open normally kept in the feed tracks, so that if anything goes wrong, any clogging happens within the part feeder feed track. So, you can quickly have the access. So, to have the access, they are actually open, all right, or you can have the easy access by opening this lead, for example. Okay. Here you can see that there are windows, and if these windows will not help, in that case you can quickly remove this casing, okay, this cover, and you can have the access, so that this clogging can be removed. Now, how to design the feed tracks and what kind of feed tracks normally we have, let us see. So, feed track design is crucial, because you have to first of all find out the actual diameter or the space inside the feed track, so that the parts are not reoriented inside while going, because we have ensured that within the feed track the part is in the right orientation. So, while going, the part feeder space should be such that the part is not reoriented, all right, and also it can have the easy access to the workhead, which from after the ball feeder it is going to the workhead. Easy access means, what I mean to say is that it can actually smoothly go through that and does not get clogged. So, part feeders are basically of two types. One is of vertical delivery of parts, where we use actually the gravity for parts to fall, or we can have a horizontal delivery of the parts. Okay. Here this is the schematic diagram or the line diagram of the feed track. The parts are coming from the feeder and it is going to the assembly, to the workhead. So, in between we have the feed track, and through the feed track the parts are going like this. Here it is the sectional view, this XX section is here, and they are going to the workhead. This is open space for the easy access to the parts, and here it is the vertical delivery of parts, where the parts are falling down by gravity. So, for the vertical design, the time of delivery Tp will be given by the time taken for a part to fall its own distance, own length, equal to its own length. So, for example, in this case, okay, what we are having is the Tp is equal to 2 L by G root over. So, this is coming from earlier we have said that L is half a t square, okay, and therefore, the t square is 2 L by acceleration, and t is equal to root over 2 L by acceleration. This acceleration is, in our case, it is the gravity, right. So, therefore, we are using this L is the part length and G is the acceleration. So, according to this equation, 2 L by acceleration root over, this will be the Tp, which is the time taken for a part to fall, and that will be the distance of its own length from the beginning to the end. Rest of the things we will discuss in the next class. Thank you very much.